Today's video is on the disk method. It also encompasses the washer method, and we'll talk about that as we move along. Tomorrow's video will be on the shell method, which is another way of doing volumes from solids of revolution. But we'll talk about when to use each method as we move on. Today, we're going to talk about the disk method. The disk method is something that happens when we have a solid of revolution. So solid of revolution is something where we have some sort of curve and we want to rotate it around either an axis or a line. So let's say, for example, I have this curve f of x and I want to rotate it or revolve the entire curve around the x-axis. If I wanted to revolve the entire curve around the x-axis, there will be a resulting volume that shows up. So in prior units, what we have done is we have found the area between f of x and the x-axis. What we're going to do today is if I take this entire area and I sweep it around 360 degrees, there will be a resulting volume that goes along with it. So it should look something like a vase when we're all done. And obviously, this is not the greatest drawing in the world, but you kind of get the idea. You take this curve, you sweep it around 360 degrees. It does not really matter whether you go counterclockwise or clockwise because you'll end up with the same resulting figure. One thing that you do need to be aware of is that in the disk method, we are slicing our figure perpendicular to the axis of rotation. And what happens when we slice our figure perpendicular to the axis of rotation is we find out that all of our cross sections are circles. Circles does not start with an S. It still doesn't start with an S. So our cross sections are circles. These cross sections are circles, which means they have a radius. Now this radius, as you will note, is changing based on the height of f of x. So in this particular case, r is identical to f of x, but that will not always be the case. So just be aware of that, and as we move along, we will figure that out. So if I want to find the volume of this, I'm going to use an integral, but before I do that, I want to think a little bit out loud. So the area of each of these circles is pi r squared. Once again, r is changing, and that's based on the height of f of x, or it's based on the actual location of f of x and what each of these r values is. But the area of each of these circles is pi r squared, and then I have to account for how far I'm going. So if I'm going from A to B, I want to take the integral from A to B, and then I have pi r squared, and then I have to account for this distance from A to B, that's dx. And that's something that we learned with Riemann sums as we were going along. But this is basically what's going on. And in this particular case, I would replace r with f of x because f of x is exactly the length of r in this problem. So if I wanted to find the volume of this in this problem, I would say pi times the integral from a to b of f of x squared dx. The disk method, once again, is what you use when we are having cross sections that are perpendicular to the line of rotation. There are two different things that happen with these types of problems where we will use perpendicular cross sections that are circles. They are disks, and that's like the problem that we just did. Or we have washers, and washers are what happens when we have, for example, a function f of x and then another function g of x, and we want to find the volume of the area between these two curves when that is rotated or revolved around a line. What you're finding is that you would have thickness in the middle, just like a washer, and a lot of the other parts would not really have much thickness at all. So you will hopefully be able to see that a little bit better when I don't have to draw it. All right, let's get into the technical aspects of this, and then we will do some example problems. The disk method. This is what happens when we are rotating or revolving one curve between that curve and a line, and we have one radius. So when we have one radius and we don't have two radii that we have to subtract from each other, we end up finding the volume of the entire region between. So if I'm revolving this entire thing around a line or an axis, I'm finding this entire volume all the way in as I do this 360-degree sweep. And notice one of the things that we see about these pictures is that we can take essentially these little discs that are going on, and we're stacking them all on top of each other, just like we would have a Riemann sum. These things do not always have to be put around the x-axis or the y-axis, and we'll see that when we get to example 2. But for right now, we'll just kind of deal with an axis. If the cross sections are perpendicular to the x-axis, that is the same thing as the line y equals 0. We also could have cross sections perpendicular to y equals some number. It does not have to be an axis. In this case, what we're doing, just like we did earlier, we are taking the integral from a to b of pi r squared, and then we have some kind of dx. Now, oftentimes, r, in this particular case, is just a function, especially if we're doing it around an axis. But we have to be sure that our radius is actually the radius of the circle, and that's going to come into play as we move on into example 2. So in this particular case here, where we're rotating it around an axis, r is exactly f of x. So we would have the integral from a to b of f of x squared dx times pi. If they are perpendicular to the y-axis, or the line x equals 0, or x equals some number, we have the exact same situation where we make sure that the radius is exactly what it is, but we have dy. These are because the cross sections are always circles. And in this particular case, if I'm rotating some kind of function of y around the y-axis, and I have something that kind of looks like a bowl or something, this would be f of y in the spot where there's r. So it would be f of y squared, but that's not always the case, and we will show you what's going on as we move along. Okay, the washer method is what happens when we have two functions. And when we have two functions, and we're just finding that little area in between those two functions, and then we sweep that area in a 360-degree, basically sweep around an axis or a line in order to find a volume, what we end up with is a picture that looks something like this, where all the way around there is some kind of thickness to it, but there is a hole on the inside. And when we get to problems 4 and 5, and actually problem 3, we will be able to see things with washers. Before we write things in the box, I'm going to talk about what's actually happening in this particular problem. In this particular problem, when I rotate this, what I'm actually doing is I'm rotating this entire thing, which is going to be a radius of f of x. So that is pi times the integral from a to b of f of x squared dx. Remember, it's squared because pi r squared is the area of a circle. And then I'm rotating this entire thing around, and I'm subtracting it. So it's pi times the integral from a to b of g of x squared dx. And so what happens when I subtract the green from the red is I end up getting just this small section that ends up being rotated around, and it's an entire volume. Notice that the bounds are the same and the pi's are the same, so I can actually combine these into one thing. So it's pi times the integral from a to b of f of x squared minus g of x squared, the quantity dx. However, I'm going to make a little adjustment to this, and I'm going to call it r squared minus r squared dx. And the reason why I'm doing that is because the radii will change based on where the line of rotation is, or the axis of rotation, and we're going to talk about that as we move along. So r, like big R, I'm going to call that the big radius, and little r is, of course, the little radius. If things are perpendicular to the y-axis or some x equals line, it would be pi times the integral from a to b of big R squared minus little r squared, the quantity dy. All right, now that we did all that, now it's time to do some examples. Find the volume of the solid created by revolving y equals square root of x on the interval from 1 to 4 about the x-axis. So in order to do that, I'm going to try and use as little of my drawings as possible. So if we take a look here, I graphed square root of x from 0 to 4, and then I just graphed it from 1 to 4. So if we kind of cut it off at 1 to 4, that's what it looks like. Now, in order to revolve that around the x-axis, remember what we're doing is we're taking that area from the square root curve to the x-axis, and notice that when I graph this in 3D, x and y are kind of flat on the ground and z's going up. I did that just so that you can kind of see what's going on in 3D. And plus, when you get to college and you have to do 3D graphs, a lot of times it's going to look like this anyway, so you might as well get used to it. And then if I take that and I rotate this around the axis, I end up with something that kind of looks like a lampshade when I'm all done, but it would be entirely filled in. So this is hollow, so you can see through a little bit, but it would actually be entirely filled in. So it would look something like this, except it's not just these 4 things that are filled in. The entire thing would be filled in. That's the volume that we're trying to find. And so if I try and find what happens when I take this and I move it around, when I move it around the axis down here, I have to actually look at what the radius is all the time. And in this problem, the radius just so happens to be f of x. So what I would do is I would take pi times the integral from 1 to 4 of f of x squared dx, because that ends up being my radius the entire time. So 23.562 is the answer to number 1. And that's because if I take pi times the integral from a to b, a is 1 and b is 4 in this problem, So once again, that's not what the curve looks like. If I graph the square root function, what's going to happen is my radius is at all times f of x, and then when I rotate it around, it's going to look kind of like a lampshade as I move along. So that's square root of x squared dx. This problem you can actually do by hand because you should know how to take the integral of x dx. You would end up getting, and I'm going to again do this in the interest of time, but this is 15 halves times pi, but you can do that by hand. Now, in example 2, what happens if I rotate this around the line y equals 4? Now, that ends up making everything totally different, and we're going to go back to Desmos and kind of see what's going on. So if I rotate this around the line y equals 4, my radius changes completely. So instead of this looking like that, where my radius is exactly the height of f of x, I'm trying to find out what happens when I rotate this area around the line y equals 4. So if I look at the radius is totally different than when it was here. The radius is now 4 minus f of x. So if I look at the height of my green area from x equals 1 to x equals 4, my height completely changes. The height is now 4 minus f of x, and I'm going to call that the radius of my circle. So if I'm looking at the rotation, when I rotate this around, it's going to now, again, kind of look like a lampshade. But when it looks like a lampshade, the smaller part is now going to be on the right side, and the wider part will now be on the left side, because when I'm looking at this area here, this part has a wider radius than this one, so as I rotate it around, it's going to end up looking a little bit different. So when I integrate this, I have pi times the integral from 1 to 4 of r squared dx. And when I look at r, I have to be careful. R is now 4 minus f of x, and then that whole quantity is squared. So remember, you want to square the radius. You don't just want to square f of x. So it's 4 minus f of x squared. And so my answer is 57.072. So you can write this down on your paper. It's pi times the integral from 1 to 4 of 4 minus root x squared dx. And then that's 57 point whatever it was. You can go back in the video if you need to look at it again. Okay, example 3. Find the volume of a solid of revolution when the area between the curves f of y equals y squared over 4 and g of y equals root y is revolved around the y-axis. So you might want to make some kind of drawing on your paper as you do this, but I'm going to spend most of the time on Desmos because it's hard to draw on the smartboard anyway. But if I'm looking at this problem, what I have is I have these two curves. So the first thing I have to do is find the intersection. The intersection of f of y and g of y, I would do by hand. I would set these two equal to each other, square both sides probably. So I end up with y to the 4th over 16 equals y. When I solve, I end up with the intersection being the cube root of 16. So that's 2.51984, somewhere around there. Okay, so essentially what I'm now doing in this problem is I'm revolving it around the y-axis. So I want circles that are perpendicular to the y-axis, which means I need things in terms of dy. And so what I'm going to do is I'm going to look and I'm going to rotate this around the axis. This actually should probably be blue to make your life easier. And then this should be red to make your life easier. But I'm going to rotate this around the axis. And then I'm going to subtract what happens when I rotate the red one around the axis. And so when I take the blue one around the axis and the red one around the axis and I subtract them, I get what happens when I just have this black area rotated around the axis. And you can kind of visualize what's happening. It would basically be a cup. So if I just took the blue one, rotated around the axis, that would be a cup basically. With it wouldn't be a very stable cup, but it'd be a cup. And then I'm drilling, and the cup would be entirely full. And then I'm drilling out part of it. So everything that's in red would be drilled out as I rotate it around the y-axis. And what I end up with is just like something that would appear to be about 1 finger's width wide at its widest point all the way around. So that's kind of what is going on as I rotate this around the axis. But in order to find that volume, what I'm going to do is I'm going to take the big radius squared, and the big radius is going to be g of y because that's my furthest curve out from the y-axis. So from the y-axis all the way out, my furthest one, my biggest radius, is the blue one. So that's going to end up giving me g of y squared, and then I'm going to subtract f of y squared because that's subtracting the smaller radius, which is y squared over 4 in this case. So then I do pi times that, and I end up with 5.984 as my answer. So this is what you'd write down for number 3, what's going on there. And I'll try and draw something real quick. If I rotate, if I make one circle here for both of them at the same height, and the smartboard makes this so hard because the calibration is really hard to get right. But you can see how this would be a washer because there's a wider part that gets kept, and then that part on the inside gets drilled out. And so you have only this part all the way around getting kept. And I know, again, it's hard to see. But if you're really struggling with it, that's why we have the flipped classroom. You can ask your teacher and they can really spend some time with you on it. Okay, the next 2 examples. Find the volume of the solid created when the area between these 2 curves, f and g, on -2 to 3 is revolved around the x-axis, which is the same thing as y equals 0, and y equals -1. So first, we'll deal with the case where y equals 0. So if we deal with the case where y equals 0, what we're doing is we have this area that's getting swept around to the bottom, and then we're subtracting the area in blue, which then just gives us the area in black. And then that area gets swept around and it forms some kind of solid with a hole in the middle. Now this hole is actually pretty easy to draw. The hole in the middle has a constant radius the entire time. So that's actually kind of easy to draw. This actually, it kind of looks like a sideways nuclear plant, the way that you would think of a nuclear plant from maybe The Simpsons or something. It looks kind of like that, except there's a hole drilled out in the middle. And so if I want to find the integral, I would do the integral from -2 to 3 of my big radius is going to be f of x, because it's going from f of x down to 0. And then my small radius is g of x. And then that, oh no, my parentheses were not wanting to listen. Dx. So I'd end up with 63.513 as my volume of this going all the way around. Then I have the second case is what happens if it's going all the way down to -1. So if I'm rotating it around the line y equals -1, Let's make that purple. If I'm rotating it around the line y equals -1, notice that the hole ends up getting bigger. Um, so the hole ends up getting a lot bigger between the blue and the purple. And so that means that even though this area is the same, it's getting swept out over a larger distance. And so my washer should end up with more volume. And so that's going to be pi times the integral from -2 to 3. And this is where we have to really be careful because my big radius is now no longer the length of f. It is now the length of f, oops, plus 1. So as you see, it's f, and then I have to add 1, which is kind of the same thing as f of x minus -1, which should make sense because it's being revolved around y equals -1. So my distance is going to be from top to bottom, f of x minus -1, which is the same thing as f of x plus 1. That is my big R. So that is going to have to be squared. That entire thing must be squared. So if I'm writing it out, it's 0.1 x squared plus 2 plus 1, which ends up being 0.1 x squared plus 3. That ends up being squared. So this is now my new R, 0.1 x squared plus 3. If I'm looking at G in this problem, G is now no longer just 1. G is now 2 because it's going all the way down to -1. So G is not actually 2, but the radius that's associated with G is now 2. So if I'm looking at the G of x radius, or little r, that's going to be 2 squared. So little r squared will now be 2 squared. So if I'm going to do pi times the integral from a to b of big R squared minus little r squared dx, I have to be careful. I have to make this 0.1 x squared plus 3 squared, and then I'm going to subtract 2 squared dx. Then this is likely a calculator problem because of the decimals and everything. It's not like it's mandatorily a calculator problem, but it probably would be a calculator problem on the AP test. Problem 4, this is what the washers look like. As you can see, the area is getting swept out over a 360-degree rotation over the x-axis, and you end up with this when you're all done. If you move the line of rotation down to -1, notice that it got bigger. And this is what the visual will look like. So if I look at this, I would have to do f of x minus -1, which is the same thing as f of x plus 1. That quantity is squared. And then if I'm looking at this, I have g of x plus 1. That quantity is squared. And so notice that my volume gets a lot bigger. It's 102.259.